possibly little later. All right. So, guys, I hope everybody can hear me and see the screen, and maybe we can start with few questions from your side till others join, and then maybe I can give an overview about what the course is about and other general questions, answers to general questions. So anyone has any questions in particular they want to raise, please unmute yourself and speak, or put it in the chat window in case you are unable to speak up.
Can I ask a question?
Yeah, go ahead. Yeah.
Actually, there was a textbook suggested by Professor Iyengar during his last this week 10 courses, week 10. Ralph B. Grimaldi, Discrete Mathematics and Applications.
Yes. Okay.
Where can we get this book? Actually, I tried Amazon, and rental services are available only in US. They are not available in India. Book is very costly.
You can buy an ebook, right? It's just a reference book. You don't have to buy the same book. There are so many other references. You can get Kenneth Rosen. That is a reasonable book for you. Kenneth Rosen, 8th edition.
Okay. The National Digital Library of IIT Kharagpur, can't it give these textbooks?
No, see, I don't know about that. See, I can only give you suggestion about what book is good to read. Okay. Whether that particular guys will give you is not, I don't know, first of all, and I have no idea. See, this is another reference, Kenneth Rosen, 8th edition. It have a e-version possibly also. You can have a look at this book. It has most of the content of discrete math course, what we do. Okay. Yeah, maybe the group theory part is not there, but even in this version, it is not much. It's okay. So you can look at this book. I think the name of the book is, the author's name is Kenneth Rosen.
Okay.
So thank you. Maybe I'll just tell what is the title of the book. Discrete Mathematics and its Application.
Thank you very much.
Yeah. Yeah. Any other questions? Any other question, guys? Guys, okay, so whoever is, okay, there is some chat questions, okay. Which type of question will be in exam, weekly assignment level or higher than that? See, first of all, you need to understand, you don't have to worry about the difficulty level or anything. As long as you understand the concept, you should be able to answer these questions. So we cannot even quantify the difficulty level of an exam or a particular question. Okay, so Sachin Kumar has asked which type of questions will be in exam. So all questions will test your conceptual understanding. Okay. If you are able to clearly understand the concept, so how many more sessions? I don't think there'll be any more sessions before the exam. Live session, you mean, right, Shashikant? Yeah, no, there won't be any more live session. This is, see, the live session, the main, the reason for this session is to ensure that you can clarify your doubts, which you could not get using the online, the video lectures. So video lectures are just recorded, no? So you don't have an interaction with the faculty. So that's the reason. This is for, yeah. Please take one session before the course is not still complete. See, what do you want me to do in the live session? There is no question asked typically.
So there is one thing. We have the discourse forum as well, right? So many of the questions are answered there each and every day. So maybe that is one of the facilities that can be used as interaction part.
Yeah. Is it okay, guys? Yeah, NPTEL video is sufficient certainly, but you will have to do some problems from the book. Like even Kenneth Rosen has a lot of exercise problem. There's a lot of noise coming. Guys, someone is unmuted. Please try to mute yourself and speak if you are speaking something personal. Okay. Many people in the meeting. Okay. All right. Okay. So if you have a question, please unmute yourself and speak. Okay. Otherwise, mute your mic. All right. Now, what was the question asked? Is a video. Yeah, NPTEL video is sufficient for the exam, but it is better to go through this book reference which I have given and then look at some of the exercise problems, work out these problems. And whenever you have doubts, it is important that you guys discuss during these sessions. That was the point, right? There is no technical question coming till now, as far as I understand. Okay, this is all mostly general questions. So are there any technical questions first you guys want to go over? Okay, maybe we can finish the course logistics also. I'm fine with anything. Just let me know.
Can you summarize what are all the proof techniques we have in this discrete math course?
See, okay. Maybe I will just summarize the discrete math course itself once. Okay, that will be okay, right? Or you want to only summarize the proof techniques? That itself is sufficient.
As you wish.
Okay, good. See, a discrete math course essentially is a fundamental course which is going to be used everywhere in computer science. As I don't know whether last time you were there, I told you that discrete math is going to get applied in 3 different ways. One is the systems. Computer science can be broadly divided into system side and then theory side and intelligent system side. Maybe I mentioned this in the last time. I don't remember. Okay, so those who had already attended, okay, yeah. So, so the system part, what do you study in system? How does a computer work? How does one computer interact with other computers and things like that? And theory is about understanding what is the, how, so theory, you learn the algorithms, and then you see whether you can write a polynomial algorithms. If you cannot do it, you will have non-polynomial. So you will study about complexity.
हमारी क्लास में 73 बच्चे हैं पर सारे ब्रांच
guys you are unmuted.
सबने ज्वाइन करनी है सिर्फ 4 ही ने रखी अभी तक तो भी
someone is speaking, please mute yourself.
Done, sir, done.
It's done. Okay, thank you. So basically, and theory talks about what kind of algorithms you need to do on these systems, and if they are not polynomial, you study the complexity and things like that. And you have intelligent systems, which talks about artificial intelligence, machine learning, and higher level applications. Okay, so in all these branches, discrete mathematics is very essential. What is the core of discrete math? It has many things, but main idea is about counting. Okay, the fundamental thing in a discrete math course is to understand how do you count. Even for this, we need the following thing. So for counting, the basic on which all of these things hinges is set theory. Second is logic, and you have the counting principles. And there are other modules like group and number theory, which not much is done in this particular course, but you can go into more details. Okay. And finally, the graph theory. These are the 5 essential modules that cover in this course, right? So set theory and logic gives you the foundation using which you will be able to apply the various counting principles. Okay. And there are advanced counting techniques that you study as a part of the counting course. For example, you study generating function method, you study principle of inclusion, exclusion, you study recursion. So these are other ways of doing counting. Okay. So let me just get into the place where he was alluding to logic. Essentially, he's saying logic is a way in which you try to prove certain statements. Now, what are all the different techniques for proving? One, we have direct proof technique. So in a direct proof technique, so you are trying to prove that some P imply Q, let's say. So we using the P is the hypothesis and Q is the conclusion. Okay. So P is, 1 second. Give me a minute. Okay. So using the direct proof technique, you using the assumptions you prove the conclusion using the hypothesis. You conclude. So that is a direct proof technique. And then, 1 second, guys. Sorry. Right. So in the direct proof technique, you using the hypothesis, you make a conclusion. So that's why you do the. So for example, suppose x is even, you want to prove x square is even. Then, so x is even, then you can write x is equal to some 2 times y, and therefore x square is 4y square. So therefore it's an even number. So that's the direct proof technique. Okay. And 1 second, this pen seems to be not writing. All right. And in indirect proof, you want to prove the same implication. What you do is you prove the contrapositive statement. That is, you prove that not Q imply not P. An example of this will be, suppose n is equal to some AB. If a number n can be written as a product of 2 numbers, then either a less than or equal to root n, or either a or b less than or equal to root n. Okay, so that's the second one. If you try to do it directly, it doesn't work out. So you prove that, suppose it is not true, that means P is false. So you have to, then you prove that then n will be less than AB. So therefore n is not equal to AB. Then Q is also false. So that's how you prove it. So sorry, I mean some Q is false, which means that both A is either less than or equal to root n, or B is less than or equal to root n, which means both A and B are greater than root n. Therefore, AB product will be greater than n. Okay. Therefore, n will not be equal to AB. So that's how you prove this indirectly. Okay. So the third technique is proof by this is second one is also called proof by contraposition. This last one is proof by contradiction. So what you do here is, if I have to prove an implication P imply Q, so what you show it, this will imply, suppose, so this implication is a logical statement. Now, if you assume that this is false, that means not of this is true. If this is false, P imply Q is false, it will lead to a contradiction. C is a contradiction here. So this is the proof by contradiction. So these are the basic techniques using which you can prove some implication. So I hope I answered your question. Someone was asking this, right?
Thank you.
Yeah. So there are other techniques like, so you are clear, or you want more clarification here?
No, it's fine.
Yeah. So there is other thing which you have, the proof by mathematical induction, which is a generalization of direct proof technique actually. So, but it's itself a new idea, right? So that's a proof of mathematical induction, right? Okay. Yeah. So anything else I would like to add here? These are the techniques which we do in the course at least. So it should be fine, I think. Yeah. Any other question, guys?
So there's a question in chat that kindly explain us the simplest way to identify a function like injective, bijective, surjective in a given question, reference to assignment 5. In general,
what do you mean by, okay, why is it so difficult? Can you give an example? Whoever is asking this question, Rama Krishna Raj, why are you finding it difficult to find out whether a function is injective, bijective, or surjective? What is the problem? Guys, no, what was the problem exactly? Why is this a problem? Explain the simplest way. Like, so see, take an example, f of x is equal to x plus 15. Okay, now this function, whether it is injective. So now first question is, what is the domain? What is the codomain? Based on which everything matters. Okay, suppose your domain is real numbers, and codomain, let's call it codomain. I'll just write it like this. It's also real number. Now, is it a one-to-one function? Guys, can you tell me? Is it a one-to-one? Ramakrishna, is this a one-to-one? See, please answer to this question. F of x is x plus 15. I have the domain as real number. Codomain is also real number. Okay. Now, is it an injective function? Yes. Okay. So first thing it is one-to-one. Second, is it onto? That means given any y, will it have an image? So the answer is, so it will have a pre-image. So y, if you say x minus 15 is a pre-image, so it is also onto. So this is an injective function. One-to-one means injective. One-to-one is so it's actually one-to-one and onto. So you call it bijective. So injective means it's fine. Into, okay. So one-to-one is injective, onto is surjective. So you have a bijective function. Is it okay? So you just have to see whether multiple values are going to the same value. If that is happening, then it is not one-to-one. And if everything in the domain is covered, codomain is covered by somebody in the domain, then it is going to be surjective. So if both are true, then you are going to call it as a bijective. So just you have to verify this. I don't understand what makes it difficult. Unless you specifically give a question, I won't be able to answer this more than this actually. Which question you are talking about and why is it even difficult for that matter? See, I don't know which question you are alluding to. Question 1 and 2, what are they? I don't know. Akash?
Yes, sir, yes.
Yeah,
so,
what question is he talking about?
Yeah, so the function is from R to R and the function x square plus 2. So we are asking that which of the following statements are true? Function is not injective, function is bijective. Is it surjective or is it not surjective?
No, this is a very simple question. No, why is there even a confusion? See, if I put two values, -1 or 1, the answer is going to be same. Therefore, it is not injective, is obvious. It is not injective. Because if you put -1, it will give 3, and 1 also it will give you 3. Is it surjective is a question. The values are only be real to real, no?
Yes, sir.
If it is real to real, then all the numbers are positive. X square plus 2 is positive. So a lot of things in the codomain are not taken by any. So it is not surjective. Over, no? What is so difficult about this question? Is it clear now at least, Ramakrishna? So just analyzing. Okay, fine. Is there any other question, guys?
So Shashikant is asking to explain cut vertex and cut edge.
Okay. See, I think I will have to also quickly look into the definition. I don't think I'll be able to recall it right away. Okay. Cut
Can
vertex.
I answer? Can I answer?
Yeah, sure. Go ahead.
Actually, if you have a graph with n vertices, and if there is a vertex, by removing it disconnected, then becomes a cut vertex.
Okay.
Similarly, cut edge means if you remove the edge, the graph should get disconnected. In which case it will have multiple components.
Right. Okay. Fine. I hope that clarifies your thing, right?
Yes, sir. So there is a question, sir. I've found difficult to recurrence relations. If you can give some examples to how to calculate recurrences.
What is that?
Recurrence relations,
In the recurrence relation, what is that you want to understand? I'm saying.
If you can. Or should I share some question?
You can ask a question. That will be better. Okay.
Okay.
Otherwise, you want to give a general example, is it? You want me to give an example in recursion, how to write recursion or how to solve the recursion?
Yeah. How to proceed?
Okay, maybe I'll tell you the following. See, let's consider the following thing. So you have a set 1 to n, okay? S is equal to 1 to n. My question is to you. This is my original set, okay? Now, I'm asking how many subsets are there for this set. Can you tell me?
2 to the power n.
Right, very good. How many subsets are there for S? Okay, 2 power n. 2 power n. Answer is good. Now, my next question is, how many subsets are there which do not have consecutive numbers? How many subsets are there such that consecutive numbers are not present? Yeah. How do we do it? So it is slightly difficult question. So let's try to use recursion and solve it. Let an denote number of such subsets. Is this okay? Number of such means those subsets of having 1 to n elements such that they don't have any consecutive elements. So I'm denoting that as an. Okay. Now, in an, there are 2 types of sets. Okay. So what are the 2 types? The nth element is included in a subset. The nth element is not included. Is it okay?
Yeah.
Okay. So how many subsets are there such that the nth element is not included? You tell me. So nth element, I throw it out. How many elements are there? 1 to n minus 1. So how many such subsets of 1 to n minus 1 will be present by definition?
We can replace n to n minus 1 like.
No. Please understand what I'm asking and answer to that. See, an denotes all possible subsets of 1 to n. Is that okay?
Okay.
Now, I'm saying in those subsets, how many subsets are there which do not contain element n in it? Okay.
Okay.
So if an element n is not present, that means how many subsets are there from 1 to n minus 1 is what we are asking essentially. Correct?
Okay.
So how many such subsets are there? Is it not an minus 1?
Yeah.
Right? Okay. Okay. So now I'm saying the next is the nth element is included here. Okay. Right?
Yeah.
So since nth element is included, n minus 1th element should not be included. Because consecutive entries are not allowed. Correct? Is it clear?
Can you repeat once again?
See, I'm saying the nth element is included in that subset. Okay.
Okay.
If that subset contains nth element, can it contain n minus 1th element?
No, because they are not.
Yeah, they are not allowed by definition. So you are going to have elements from 1 to n minus 2 alone now, and then n will be put on that subset. Okay. Yeah. So how many subsets are there from 1 to n minus 2? That is an minus 2. In those subsets, I'm going to just add nth element. So therefore, an is nothing but an minus 1 plus an minus 2. This is a recursion. Is this what you're asking?
Yeah.
Now you understand, right? How do we write the recursion? Is this how did I write this? Is this clear or not clear? Please tell me.
Yeah, I mean, you just,
okay, let me just, maybe with an example, I'll clarify. So let's take an example 1, 2, 3, 4. Okay. This is what is my original set. Yes. Now I'm asking how many subsets are there which do not contain consecutive elements. So let's first list it down. What are they? 1, 2, 3, 4. 1, 2, is it possible?
No.
Guy, no. 1, 3 is possible. 1, 4 is possible. 2, 4 is possible. Anything else is possible? Anything else is possible?
No.
No. Okay. Now my question is, how many of these totally 1, 2, 3, 4, 5, 6, 7 are there? Okay. In these 7, out of these 7, how many of them contain 4? How many of them do not contain 4? Tell me. So let me write it down. Do not contain 4.
So 4 sets and which contains are 3.
Yeah, do not contain. Let's list it down. List it down because do not contain 4. 1, 2, 3, 1, 3. Right? Contains 4 is this. 4, 1, 4, 2, 4. Correct? Is it clear so far?
Yeah.
Now, do not contain 4 is essentially how many subsets are there from 1 to 3. So that is nothing but A3. Okay. So this gives rise to A3 because there are 3 elements. Now, contain 4 will lead to A2. Why? Because you take any subset, 1 and 2 only, you take all possible subsets, you just include 4 in it, simply, because you should contain 4, no? So the A2 number of subsets are there, which contain 4. A3 number of subsets are there, which do not contain 4. So A3 plus A2 is equal to A4. That is how we get the recursion. Is this clear?
Got it now.
Yeah, okay. Yeah.
Thank you.
Yeah. What else is the question, guys? Any other question? See, the live session is to get your doubts clarified. So I hope it is clarifying your doubts. And if there are any questions, please feel free to either type or unmute and speak.
So I've shared a question recurrence. Can you solve it?
Okay. So see, how do we solve a recursion? See, whatever I am talking about is how do we get a recursion for a problem. Okay. So you are asking a question, Tn is equal to 7, Tn by 2 plus 3n square plus 2. Right?
Yeah.
So what is that you want to compute here?
I mean, I want to solve.
What do you mean by solving a recurrence means?
I mean, if I can, in big O notation terms. Like,
correct, but that's true. First, I want you to understand, is this part of this course actually solving a recursion of this form? I don't think so, right?
No, sir.
This is not part of this course. See, you can certainly do it. You can look at, I will give you reference so that you can look at that reference. You can look at Corman, reversed, Lisserson, I think. There is something called master's method. You can use that to solve any recursion. Okay.
So, in masterals, I have gone different resources and there are different, variation definition of master's method. Some says that, so I don't know which definition I should follow.
No. First of all, there are multiple methods to do it. Okay. First, let me tell you one thing. This is not relevant for this particular course, but since you, because there are no other questions and you have asked this, I'll just tell you. See, whatever be the method, you can build a tree and then you can solve it using that tree. So 3n square by 2 plus 7 times n by 2 whole square. Like that, you can build a tree. So you can look at this book. I think this book has a very good reference of all the methods. So you can go over them one by one and then try to write. Okay.
Okay.
Okay. So that should be fine. Yeah.
This is the same book for algorithm, right?
Yeah, this is the same book. Kalman reverse, Lisserson reverse. I think I messed up the order. Lisserson reverse and Stein.
Yeah. Okay. Thank you.
This book.
Yeah, just the name Corman is enough. The book is very famous. You can find it.
Yeah, Corman is good enough. Yeah, correct. So there's a very clear description. Okay, you can do it. So whatever in this course, given a problem, maybe you can write a recursion, and then you can solve a recursion using the method linear recursion only. We are not looking at these kind of recursions, right? Okay. Any other question, guys?
So I think in 11th week we are also covering group theory, right?
Group 3, yeah, okay.
can you, I mean, explain some questions on group theory?
No. Is the group theory module already covered, or you want me to give a overview of group theory?
Yeah, I mean,
It is not yet covered, sir. As in it is in the week 12 content, and week 10 is going on right now. But then I guess he wants just a overview
Review.
of what is going
I
on.
mean, I'm asking because you're saying that there will be no further sessions, so that's right.
No. We will have more questions. I think the people will take time to ask the question. But anyway, I will try to answer your questions. This question first. See, group theory, we are going to, it's a bit of an abstract subject. Whatever we cover in the course is quite a small piece. Okay. It has a lot of details, and you can use it to prove a lot of theorems in number theory and all that. Okay. The famous thing being the Fermat's-Little theorem is easily you can prove using group theory. See, in a group, basically a group is a set. Okay. Group is a set with the operation in it. Okay, for example, take Z, which is the integers. Now, operation is plus operation. Now, what is the property?
So we create a combination of both, and we got a group, right?
Sorry?
We create a combination of these both, like elements and the operation, respective operation.
So, operation is essentially, you take two elements in the group. It's a Cartesian product, G cross G to a G. So basically you get two elements A and B in the group. It should give an element C in the group. So that is the first property, closure.
Yeah.
So you take two elements and you do the operation. It leads to some other element in the group. So it should be satisfied. Second thing is what? What is the second operation? Associativity. So for example, you do the operation I'm going to denote by plus. So A plus B plus C. If you do like this or if you do like this, it should not matter. The order in which you do the operation should not matter. Now means I'm not changing the elements. AB is equal to BA. I'm not saying A plus B is not equal to B plus A. I'm not saying. So you have written an expression. You can do the operation in any order. It should work out fine. Associativity. Third,
inverse
identity, existence of identity. So there is an element E such that A plus E is equal to E plus A is equal to A. Such an element should exist. Fourth one is inverse. So for every element A in G, there should exist an inverse element A inverse such that A plus A inverse equal to A inverse plus A should be equal to E. You see, here I mean plus is the operation I'm talking about. Okay, it is not plus means it's an addition I'm doing. So please bear in mind. So in this case, let's take real number minus 0. That is my set, and multiplication is the operation. I will ask whether it is a group. So if I take two real numbers and multiply, will it form a real number? That's the first property. Is it true or not? Guys, whoever asked this question, where did you go?
I think it's true.
Yeah, it's true. And associativity is also true. You can multiply the real numbers in any order. It is indeed commutative, means you can change the order of the elements also. It won't matter. And what is the identity here?
1.
1. Okay. And what about the inverse for an element A? 1 by A, right? 2 means half, 3 means 1 by 3. 0.6 means 1 by 0.6. So for any element, you will have an inverse. So this is a group. This is an example of a group. So everywhere, wherever I have put plus, you should put multiplication, because that is the operation we are talking about. So you have to represent the operation in one or the other way. Some people refer it as plus, some people refer it as a dot, some people refer it as a star. So basically a group is a set with an operation such that some properties are satisfied. These are the 4 basic properties. And if a group has an additional property that A plus B is equal to B plus A, the order in which you do the operation with the elements, if it doesn't matter, then it is called commutativity. And whenever such a property is true, then we call that as an abelian group. A group which has additional structure. So, so that is what group theory is about. So where and all these structures are there, and using this, what can you make inference? That's what we study in group theory. But an important theorem which you will see in group theory is what is called the Lagrange's theorem, which says that if H is a subgroup of, we write H is a subgroup of G, then order of H means the number of elements in H should divide order of G if H and G are finite groups. So if they are infinite groups, it doesn't make sense division. So this is an important theorem. Using this, lot of things can be concluded. So basically, it says
what is order of group?
Order of a group is number of elements in the group. That's all. If you think of it as a cardinality, order of a group is just the number of elements in the group. Okay, is it fine?
Yeah.
Okay. So I think we had a brief, quick review on group theory. But anyway, you will see this in the module 11, I assume. Yeah. Okay, or 11 or 12, I'm not very sure. Okay, fine. Any other question, guys? See, please feel free to ask as many questions to clarify your doubts. See, now in this session only, no one is asking why do you acquire one more session, guys?
Well, sir, I can say for myself because I'm not done with the course syllabus yet. So I'm not,
Sorry.
I am not done with the whole syllabus of the course subject.
No. The point of the session, why are we, see, the reason why we are all coming together is to make sure that I clarify some of the doubts.
You asked that why I'm asking another session. The reason is because I'm not done with the course syllabus yet. So I just, until I am not completed the syllabus, how can I ask for the question? That's thing.
No, correct only, but no, I understand. Okay, makes sense. Whatever you are saying is correct, reasonable. I think TAs can help you, but if you want to write up to me also, you can write to me. I can clarify your doubts in the mail. Okay, we'll see. The TAs will take it to me in case if they are not able to manage. Okay, because typically in a course, we have 2 sessions, 2 live sessions. That's how we work out. See, whatever you have covered, based on that, if you have any doubts, we can discuss that. Is that okay?
No problem.
Now, I mean, if there is no question, yes, I understand. Certainly, you have to go through the material unless and until how can you ask the doubt is reasonable, right? But the sad part is there is only 2 sessions. If possible, we'll have one more session. Okay. Yeah. What is the question on group concept? Yes. What is the question, Ashtray? What is your question? I'm not able to follow your question. Final or external is subjective or MCQ type. Ashish, can you answer them on this?
Yeah, the exam is going to be an MCQ type. There is no subjective component to it. It will be similar to the assignments that are uploaded weekly.
Okay. See, those guys who had given responses also, if there are any general questions, please ask from that. The reason for collecting the question was to see, for myself to understand what kind of questions you will be interested in. I can also prepare a little bit what is expected from me. But yeah, you can ask those questions if you had already given the in the responses also, you can bring that question and ask it right away. We have some time left, 20 minutes more. Guys, any other question you want to ask, or should we wind up the session early? You want to revise some concepts, we can do it.
So maybe can we take the question of isomorphic and non-isomorphic, the difference between them and the thing?
Okay.
It was asked
okay, good. So the question was, what is the difference between an isomorphic graph and a non-isomorphic graph? Is that what it is? See, the idea of isomorphism is to understand whether the 2 graphs are same or not. Okay, so that's what it is. So even when you study in group theory, we are going to see whether group isomorphism. There are many ways in which isomorphism will keep coming. Yeah.
Sir, should I even take this literally? I mean, like we are just taking the similarities of the two graphs.
No, not similarity. There is a clear meaning of when two graphs are isomorphic. Suppose you have two buildings, when are they isomorphic? We are asking, let us say. Like, what does that even mean? We should clearly define first. Okay. So in a graph, what is a graph? Graph is just a collection of vertex and edges, correct?
Yeah.
Okay. Now you have been given two graphs, G and G prime. Okay. Now we want to understand whether these two graphs are same or not. Now, similar means it makes it very, very vague definition. Now, when we will say G is isomorphic, let me use the equivalence thing to denote isomorphism. So, G is isomorphic to G prime. Isomorphic to G prime. When first thing is number of elements in V should be same as number of elements in V prime. That is the first basic requirement. If they are not same, then they are not even isomorphic, straightforward. Now, what we say, the edges also should be same, but that is not good enough. Now, what we are saying is, suppose you are able to give a bijection from G to G prime in the following way. So, V to V prime. F is a function which is bijective. That means from V to V prime, such that whenever you have an edge in a graph G, you should have a corresponding edge in graph G prime. So, for example, let me write the definition. So F is a function from V to V prime. So you pick an edge E belonging to E in G.
So you should have the 1-to-1 and onto both.
No, F is 1-to-1 and onto. That is not a big deal. See, F, you will always, if they're equal number, you will be always able to give 1-to-1 and onto. The main thing is, you are saying that suppose you have an edge in your edge set, then edge is having some V1, V2, right?
Yeah.
If V1, V2 forms an edge in E, okay, let me call it UV. That makes it makes life easy. So suppose UV, U comma V is an edge in G. Then F of U, F of V should be an edge in E prime. Then only we say it is isomorphic for all UV in E. Is this clear? Is the definition clear? So you pick. So what we are saying is, you have taken some edge in E. Okay, because of the mapping F, we have bijective mapping from F. F is a bijective mapping. If you have an edge in E, which is UV, then FU, FB should be an edge in E prime. That's how it should be. Then only we say the graphs are isomorphic. So just to give an example, let's take maybe these two graphs are okay, 1, 2, A, B. So this is a bipartite graph, right? Correct?
Yeah.
Now, this is your graph G. Now, G prime is the following, okay? This diamond graph. Let me call it X, Y, W, Z. Okay. My question is G and G prime isomorphic or not? This is a bipartite graph. Okay. This is not a bipartite, it's a cyclic graph. What do you think?
It should be, because
should be why? Then you should give me the graph isomorphism. What is the function F I am asking then? So tell me what is the mapping from 1 to AB to XYZW, such that when I take an edge here, they should form an edge over there. So what is 1, what is 2? You tell me. So you have to give the mapping F, no? So let me write down the mapping. It is isomorphic. If you give a mapping, 1 to AB is there. So now 1 will go to what? 2 will go to what? You tell me. 1 goes to what?
X. 1 goes to X.
Okay. 2 goes to W.
And then
A goes to Y. And finally B goes to Z. Let's take this. Okay. Now here the mapping, giving this mapping is not sufficient. You will be able to give always If there are 4 nodes, you can make a one-to-one mapping. That is not sufficient. Now you take one is if there is an edge present, that it should be present there. If the edge is absent, it should be absent there. That is what you have to check. Okay, both ways we have to check. Now you picked 1, 2 now. Okay. Now what is f of 1, f of 2? Hello?
Yeah, X and
W.
W.
Is that an edge here in the other graph?
No direct edge.
Okay, so 1, 2 didn't have an edge. XW will not have an edge. Okay, so first thing. Now 1, 2 is not an edge first. Does not belong to E. So this also doesn't belong to E prime. Okay. Now 1A, you take it. Belongs to E. Correct?
Yeah.
F of 1, f of A is what? Is nothing but f of 1 is X. F of A is Y. XY belongs to E prime. So whenever you have an edge, it should become an edge here. That is when you are going to say that. Is this clear?
Yeah.
So when we say 2 graphs are isomorphic, what we are saying is, whenever you have an edge in this graph, then when you map that edge to another edge, so when you map that edge, then that also should form as the edge in the other graph. So that is what is happening. Therefore, these 2 graphs are isomorphic. Okay.
Okay.
I hope I answered your question.
This is not my question.
What is your question?
I only asked.
Okay, it was not your question. Okay, so whose question was this?
Sir, it was in the Google Forms.
Oh, okay.
Yeah. So one more question. Someone is asking to prove that paper folding example. If a paper is folded 40 times, then the thickness is equal to the distance between earth and moon. So can we prove it on paper?
Okay.
That is one person's doubt.
See, the thing is, it is very okay. So when you fold a paper, right, there's nothing to prove here. What happens essentially? Tell me. See, you can verify this. What you have a paper, take a paper, and suppose the width of the paper is something, W means the thickness of the paper. Let's say T, we will call it.
So we can't tear it for after 4 to 5 times more than that.
No, that is all theoretically only we are asking this question. First, you understand that. See, first of all, what is meant by folding a paper? That's what let's construct a mathematical thing. Yes, it is true that you will be able to reach the moon, but whether we can fold more than 6 times in a practical scenario, no, not possible. Okay, how much ever huge paper you bring it, more than 7, 8 times, you cannot do it. Okay, so that's a practical difficulty. But let's first understand what is the question trying to tell us. Okay, so you have a paper of some size. Okay, it is not about the size of the paper which matters. It is the thickness of the paper which will matter. Okay, now if I fold this paper, what is going to be its thickness? Guy, tell me.
Just
What
double.
is double, no?
Yeah.
So if T is 0.001, then 2T is 2 times 0.001. Now, if I fold it one more time, maybe I didn't do it as a proper half. It should have been little more perfectly. I should have drawn. Sorry. Okay, so the half thing is like this. It comes. Okay, so it becomes 2 times T. Now, if you fold it one more time, it becomes a. What is the thickness of the paper now? It becomes. Yes. 2T will become what? I'm folding it again.
40 square?
No. 2T will see. This is the thickness now. 2 times the thickness. That's all. No, 2 square T. Correct.
Yeah.
2 times 2T. That's all. Whatever you told earlier, T was there, 2T it became. 2T was there, 2 times 2T became 2 square T. So if I fold it, so this is for T, one time folding, 2 time folding. If I fold it n times, what will it be thickness?
T.
2 power n times t, no? N times. Is this clear?
Yeah. So the growth is exponential.
Sorry?
So the growth is exponential.
So the growth is exponential. That's all we are trying to tell by this example. Okay, nothing more. So growth is exponential. So you take t is equal to 0.001. And how many times you are supposed to fold? They have told n for touching the moon. 30 times, is it?
Yeah.
40 times. Sir has mentioned it as 40 times.
Okay, so that means we are saying 2 power 40 times t will be greater than distance between man and earth, the distance between earth and moon. That's what it means. You can verify that using a calculator. 2 power 40 is a huge number. Okay. T is 0.001. Even after 1000, 2 power 10, it will go away. That 1000 into 1000, it will be like 1. Then 2 power 30 more times is there. By the time you will reach whatever kilometers or meters, whatever is the way they will, you can verify it. This is okay. So that is the meaning of folding the paper to reach from earth to moon. Basically, every time you fold, you are going to double it. Okay. So the power of exponential is so much is what this example is illustrating. But practically after 6 or 7 steps, you will not be able to fold the paper. All right. Any other question, guys? Am I audible or?
Yes, you are audible.
Yeah. Okay. Any other question then? Okay. If there are no questions, we can wind up. Should we wind up or what? See, we have 10 minutes. You guys can utilize this time well if you want to. I know some of you have not prepared, but that is the whole purpose, right? We gave you sufficient time to prepare. Any other question is there which we need to discuss, Ashish, right? Some other question was there, right? What else?
Yes, sir. So in general, people are asking why is graph theory so important?
Oh my God. Okay. Yeah, it's a good thing. See, graph theory is going to be extremely a useful course. Okay. See, first of all, many things in the practical thing can be represented as a graph. For example, map is represented as a graph. There are some application of graph coloring. Many search problems are represented as a graph. Then you apply breadth first search, depth first search. Many AI tasks, artificial intelligence tasks requires the first representation as a graph. And for even in a graph, how do we represent it in the computer? You can represent it as an adjacency list or adjacency matrix, or you can do incidence matrix. So there are many ways you can represent the graph. So graphs are everywhere. Road networks, you take, what is that? Computer networks. All of them has to be represented as a graph, and then you can run various algorithms, shortest path algorithm. You can run flow algorithms. So many problems can be modeled in this. So many real-life problems can be modeled as a graph, and various algorithms, computer like data structures algorithms you learn, those algorithms can be applied, and the solution is essential for a practical purpose. Okay. So, for example, easiest way to explain is take a graph. You have a graph of cities. You want to find the shortest path from one place to another place. So you first represent it and then solve it as a shortest path problem. Once you know that, you can go take the route. So I think it's a very important and simple use of the graph. And there are many more actually. This is just one I'm saying. Okay. If anyone wants to allow me to elaborate further on this, please ask further questions. So why don't you guys read? There are many applications are given in the book. You can check that Kenneth wrote a book on graph theory. Okay. That should be a good reference for this as well. Any other question?
Yeah, sir. They're asking that what is the use of Catalan number in real world, and do we need to learn Catalan series for examination? So the real world examples are discussed in the video itself, I guess.
Right.
Yeah. And it's important for the examination as well. Questions may be asked from that part.
Yeah, certainly. See, there are many sequences which are interesting. Let me just give a simple example. So let me ask you, what is the use of Fibonacci numbers? Anyone? See, we have been learning Fibonacci numbers for a long time. What is the use of it? Forget about Catalan numbers. Catalan numbers similarly has a lot of use cases. When you try to count, many things turn out to be Catalan numbers. How many matrices, how many ways can we multiply the matrices? How many ways I can parenthesize the bracket? How many ways can I triangulate a n-gon? So many such things will be turning it out to be a Catalan number. So it's automatically appearing. That is one thing. So before we get into that, what is the use of Fibonacci numbers, like Fibonacci series? Anyone?
It comes in nature, the number of leaves in a tree.
Right. So that is one of the standard. Yeah, that's one correct application. So we need to study why is it happening like this. So that is one correct application. So let me give you one simple and quick application. Suppose you go to US or somewhere where miles is the distance used. Let's say I want to find out what is 60 miles. Okay. In kilometers. What is the answer? What do you do? Miles to kilometers?
So 3 miles, 3 kilometers in a mile.
No. 1.6 kilometers. 1 mile is 1.6 kilometers. So 60 miles, you can multiply by 1.6, which is like 96 kilometers. This is a direct computation. Okay. So another easy way to do the same thing is to use Fibonacci numbers. It may look little tedious, but it's a good application. So what you do is 60 miles is there. So you write 60 as 55 plus 5 first. Okay. Now 55 is the Fibonacci number. Okay. Now for 55, you get 55 is next Fibonacci number is 89. And for 5, the next Fibonacci number is 8. So you say 89 plus 8 is 97. So this is another way to do it. I hope it's clear. So maybe one more example will help. Suppose I want to convert 90 miles to kilometers, let's say. Okay. I write this as a big Fibonacci number 89. That is the first 89. And then the next one is just 89 plus 1. So for 89, the next Fibonacci number is 144. 89 plus 55 is 144. For 1, this is 2. So the answer is 146 kilometers. So this is how you can compute. So basically, instead of doing multiplication, you can do some addition and then compute it. So it's just some practical use case I'm giving you. There are many use cases. Fibonacci search is there, where you can use, how do you search to minimize global, means a convex function. So you search it using the Fibonacci sequence. And to analyze it also, it helps. So many use of these Fibonacci numbers. So these sequences not only help you in understanding how do you do counting, but it also comes in some applications also, like this, whatever I have just described. Okay. So essentially, the Catalan number, the use of the Catalan numbers is it appears in many such computation, like how many n-node trees are possible, how many rooted trees are possible. Like that, there are many places where Catalan numbers naturally comes. Okay. So and it's interesting to study it because first of all, it gives a conceptual clarity, and anywhere such kind of recursive structure is there, you will be able to apply similar ideas. So that is the next use case. Okay. Yeah. So I think are we almost done? Like, if there are any questions, let me know. Otherwise, we can call it a day and then we can end today's session. Anyone has any further question? I can take maybe 1 or 2 questions if required. Ashish?
Yeah, sir. One question on contrapositive.
What is the question?
Yeah, they are asking to explain the contrapositive.
Okay. Okay, sure. See, whenever we want to prove P imply Q, what does that mean? This is double equivalent to P bar plus Q. This we have seen in the discrete, in your lecture you must have seen. Essentially, P imply Q is a Boolean function on 2 variables, which is P bar plus Q. Okay. Now, if I have to prove this, typically, we also know this is equivalent to Q bar imply P. That's what is a contrapositive statement. So, why? One second, sorry. This implies this is equivalent to Q bar imply P bar. The statement is equivalent to this. Because if you look at Q bar imply P, that is actually equivalent to, if you use the rule, it is nothing but Q bar imply P bar. So Q plus P bar. Okay. So you want to really say that whenever I want to show that some P imply Q, I can also equivalently prove Q bar imply P bar. That means if Q is false, then P is false. Okay. Is this clear? So P imply Q means what? If P is true, Q is true. It is also equivalent to say that P is true, Q is true means, is it P is necessary for Q or Q is necessary for P? Or what is this? So P imply Q essentially is P is sufficient for Q, right? So there's some. Okay. Yeah. Okay. So P imply Q is, in English, we can say that this means P is sufficient for Q. If P is true, then Q will be true. So we say also the same statement is also equivalent to Q is necessary for P. Both are same. There is no difference. If P is true, then Q is true. Okay. Or we are saying Q is necessary for P. If Q is false, then P is false. That's what contrapositive statement means. Contrapositive is Q bar imply P bar. If Q is false, then P is false. To pictorially describe this, you write P imply Q is the following. P is set of places where this is true. Then Q is this one. So P, if it is true, then Q will be true. Okay. Right? Because once inside, these are the places where P is true, the places what I have drawn here. And the outside places is where Q is true. Suppose the domain of P and Q is bigger. Let's say this. I have this as my omega. So this I'm trying to, this is not in the Boolean logic. I cannot work out this whole thing because it doesn't make sense. P can vary the truth values based on where it is. This works in only the first order logic. The Venn diagram, I can show it only through using the first order logic. What we are saying is, so you have a X variable, that is the domain. This place, wherever I have drawn a circle where P is there, it is a place where P is true. The proportion P is true. And the place where I have drawn a Q circle where Q is true. Now P is sufficient for Q means, now this is true, then Q will be automatically true. We can also interpret it in the following way. So this outside is Q bar, right? So if any event where Q bar is true is happening, then automatically we can conclude that P bar is also going to happen, right? Because P bar is a bigger set compared to Q bar, which contains, so that is why Q is, so this is what it is mean by implication. And contrapositive for this is the following. So these two are equivalent. That's what we are saying. P imply Q is equivalent to Q bar imply P bar. This is a contrapositive statement. Okay. Any other questions?
So one person has asked about cyclic graphs. So I guess that question should be very much clear. A graph which a path which goes which starts at a point and then ends at the same point is a graph which has a cycle, and hence it is called a cyclic graph.
A graph which contains a cycle. Basically, you will have a path or you have a sequence of vertices in which you start and end back in the same vertex. Such that so basically a sequence. See, a sequence of vertices such that vertices sequence, let me call V0, V1 to Vn, such that Vi plus 1, I equal to I is 0, 0, 1, 2, 2, n minus 1. Basically, this should belong to H. And Vn is equal to V0. That means there is a cycle. So whenever a graph contains a cycle, then you call it as a cyclic graph, right? Is that what it is? Or you want to, like, only if it's a cycle, then only we call it cyclic. It's just a convention. So basically a cycle is the following definition. If you have a sequence of vertices such that in that sequence you have it as every pair will form an edge and the starting and ending vertices are the same, then we call it a cycle. Okay.
Yes.
Yeah. So let's not worry about the conventional. So I think in the class it is defined, if it's a complete cycle only, it is called a cyclic graph, right? That's how it is defined, right?
Yes, sir. Yes. If there is a walk from a point and we come back to that point once again, then there is.
Correct. Okay. Fine.
So one generic question a person has asked, that what is the real and imaginary part behind the discrete maths? As in, I guess the complex part that person must be asking.
You are trying to. What is your question? Can you please elaborate? Whoever had asked this question, I am not able. What is the easy part and difficult part in the discrete math? Is that what I should interpret it as, or what is it?
No, sir. I guess it is the real as well as the imaginary concepts behind the discrete maths and Vedic maths, like something like a kind of abstract question, I guess.
See, these are fundamental things to count, right? The discrete math essentially is for counting. There is no complex number involved in discrete math. At least complex number, when you come, you are going to get a continuous math. Okay. All right.
Yes.
So I don't understand unless you explain what you really mean by real and imaginary parts behind discrete math. What do you really want to ask is not clear. Any other question? I think we are already running out of time, so maybe we can call it a day, and then.
Yes, sir. Almost all the questions have been covered, and the rest, the overview that you gave in the beginning was had covered many of the questions as well. So yeah, we are done.
Okay. Thank you, guys. Thank you very much. Okay. Yeah.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.
NPTEL personals, this meeting can be ended. Thank you.